our last lecture we were discussing the operator algebra involving the angular momentum operators. We had we will continue our discussions on that. We first said that the operators j square, and let me just consider the z component of the angular momentum j z, they commute with each other, and since they commute and since they are observables, we can have a set of simultaneous eigenvectors of the operator j square and j z. So, we wrote down j square ket lambda m is equal to so much and j z ket lambda m is equal to m lambda m. Then we had defined two operators j plus and j minus. J plus was j x plus I j y and j minus was j x minus I j y. And we now let me consider the commutation of j plus comma j z. So, this is j plus j z minus j z j plus. So, this is equal to j plus is equal to j x plus I j y. So, this will be j x comma j z plus I j y comma j z. Now, you know that j y j z commutator is just I j x. So, this will be I times I is minus j x, and this is in the wrong order. So, j z comma j x, as you would recall from the previous lecture, is I j y. So, j x j z is the minus of that. So, this is minus I j y. So, if I take the minus sign outside, so you will get j x plus I j y, and so this is equal to minus j plus. I hope I have done it correctly. So, the left hand side is j plus j z minus j z j plus is equal to so much. What we do is we operate this on ket lambda m, that is we operate this both sides on ket lambda m. So, you will get you have here. So, let me put a plus sign here and minus sign here, and take this to the other side. So, we will have, please see this, j z j plus. Let me do this once more. So, we have j plus comma j z, the commutator. This was equal to j plus, we derived that. So, we had j plus j z, let me leave some space, minus j z j plus, let me leave some space, this is equal to j plus. What we do is, as we mentioned, operate each term on ket lambda m, operate this on ket lambda m, operate this on ket lambda m. Then you can see that j z operating did I do it correctly? J plus Jz is equal to, oh, this was minus J plus minus. So, this is minus. I am sorry, there is a minus sign here. So, Jz operating on ket lambda m is m times J plus ket lambda m minus Jz J plus ket lambda m minus J plus ket lambda m. So, I multiply all sides by a minus sign. So, I get a minus sign here, plus sign here and a plus sign here. Now, I take this term on the right hand side. So, I get Jz operating on J plus ket lambda m is equal to m plus 1 operating on J plus ket lambda m. Thus, if ket lambda m is an eigenket of the operator Jz belonging to the eigenvalue m, then J plus ket lambda m is also an eigenket of the same operator Jz, but now belonging to the eigenvalue m plus 1. So, let me denote this by say ket p. So, Jz ket p is equal to m plus 1 ket p. Now, I do the same thing. Instead of operating this by ket lambda m, I operate this on ket p. So, I will obtain Jz J plus ket p will now be equal to m plus 2 J plus ket p. Of course, provided ket p is not a null ket. Similarly, if ket p is not a null ket, then J plus ket p is also an eigenket of the operator Jz belonging now to the eigenvalue m plus 2. Provided this is not a null ket. We had seen that J, so therefore, we had seen that J plus ket lambda m, in the last lecture we had shown that is also an eigenket of the operator J square belonging to the same eigenvalue J plus ket lambda m, and Jz J plus ket lambda m is equal to m plus 1 J plus ket lambda m. So, therefore, if ket lambda m, of course, a non-null ket, is a simultaneous eigenvector of the operator J square and Jz, then J plus ket lambda m is also a simultaneous eigenket of J square and Jz belonging to the same eigenvalue of J square, but 1 raised eigenvalue of Jz. So, therefore, J plus ket lambda m must be something like some constant times m plus 1. M increases by 1, but lambda value remains the same. I can go on doing that, then you will have J square operating on J plus ket lambda m, that will belong to the same eigenvalue of J square J plus ket lambda m but for this the same will now be m plus 2, and that is why they are known as ladder operators, provided this is not a null ket. So, the value lambda remains the same and m increases, but I have the inequality that lambda must be greater than or equal to m square. So, at some m value we must have a maximum value of m, because this process cannot go on indefinitely, otherwise it will violate the inequality lambda is greater than or equal to m square. And so, therefore, at some maximum value of m, so there must exist a maximum value of m, and let the maximum value of m be equal to j. Then this eigenket is a non-null ket, is not a null ket, but j plus ket lambda j is a null ket, because m value, the maximum value of m is j. So, you cannot have m plus 1, and therefore, j plus ket lambda j must be a null ket. So, therefore, we must have that j plus ket lambda j, where what is j? This is a null ket, where j is the maximum value of m. I operate this by j minus, and I had shown that, you remember that j minus j plus, we had evaluated this is j x minus I j y multiplied by j x plus I j y. So, this is j x square plus j y square, and this is plus I j x j y minus j y j x. So, that is I j z. So, this is equal to j square minus j z square minus j z. So, I operate, so j minus j plus this thing. So, you must understand the equation that j plus ket lambda j is a null ket. This is not a null ket, of course, this is not a null operator, but a operator operating on a ket gives you a null ket. So, I operate this by j minus. So, I get j square minus j z square minus j z operating on lambda j must be a null ket. This is a non-null operator, this is a non-null ket, but this operating on this is a null ket. Now, this is an eigenket of j square. So, the j square operating on that is lambda, the eigenvalue of j z is j. So, of j z square, if j z ket lambda j is equal to j lambda j, because this is the eigenvalue of j z, and therefore, if I operate this again by j z, so j z square lambda j will be equal to j operating j z lambda j, so that will be j square lambda j. So, this will be lambda minus j square minus j operating on lambda j must be a null ket. Now, here this quantity is a number. This is an operator, it is a non-null operator, but this is a non-null ket by definition. So, this number must be 0. So, lambda minus j square minus j, this is really beautiful, is 0, which gives me the beautiful result that lambda must be equal to j square plus j or j into j plus 1. Okay. Now, if you have not been able to follow the algebra, let me do it all over again for the j minus operator. So, you have the j minus operator, let us forget about everything, but keep this result somewhere. So, the j minus operator is equal to j x minus I j y. So, j square commutes with j x, j square commutes with j y. So, j square commutes with j minus. So, j square comma j minus is equal to j square comma j x minus I times j square comma j y. Both are 0, both vanish. So, this is 0. So, you have j square j minus is equal to j minus j square. I operate both sides by lambda m. Okay. So, we have this is equal to lambda. So, this will be lambda j minus ket lambda m. So, you will have j square j minus, thus if ket lambda m is an eigenket of the operator j square belonging to the eigenvalue lambda as expressed by this equation, then j minus ket lambda m is also an eigenket of j square belonging to the same eigenvalue lambda. Similarly, let me denote this by say ket A. So, then we can write down j square exactly in a similar way, j square j minus ket A will be equal to lambda j minus ket A. So, if I denote this by ket B, which is j minus ket A, which is equal to j minus ket lambda m, then we say please listen carefully, if ket lambda m is an eigenket of j square belonging to the eigenvalue lambda, then j minus let this is also an eigenket of the same operator j square belonging to the same eigenvalue lambda, provided of course A is not a null ket and j minus A and B is also not a null ket. And so, therefore, once again we must expect degeneracies, and this is an eigenket, this is an eigenket, and this is also an eigenket. Okay. Then we consider the commutation relation of Jz. So, let me consider the commutation relation of Jz of j minus, this is Jz comma Jx, j minus is Jx minus Ijy. So, this is Jz comma Jy. Okay. So, Jz comma Jx is equal to Ijy and Jz Jy will be equal to minus, if you look up the first thing that we wrote down, that jz comma jy was minus ijx. So, minus minus plus and I square is minus. So, this becomes minus jx. So, if I take minus sign outside, so I get jx minus ijy, sorry, ijy. So, this will be minus j minus. So, I have jz j minus, please leave some space, minus jz j minus jz, leave some space, is equal to minus j minus. Now, what I do is operate this on lambda m, operate this on lambda m, and operate this on lambda m. And you have here jz ket lambda m is m lambda m. So, I get this first term becomes jz j minus ket lambda m, and if you take it to the other side, then it will become m minus 1 j minus ket lambda m. So, therefore, if ket lambda m is an eigenket of the operator jz, if ket lambda m is an eigenket of the operator jz belonging to the eigenvalue m, then j minus ket lambda m is also an eigenket of the same operator jz, now belonging to one less eigenvalue m minus 1, provided of course this is not a null ket. And I can continue this again. So, jz operating on j minus ket lambda m. I hope you can now immediately say that this must be m minus 2, j minus ket lambda m. So, therefore, if ket, let me summarize, if ket lambda m is a simultaneous eigenket of j square belonging to the eigenvalue lambda and jz belonging to the eigenvalue m, then j plus ket lambda m is also a simultaneous eigenket of j square belonging to the same eigenvalue lambda and of jz, no, I will put minus sign, but now this will become m minus 1, provided this is not a null ket, and then j minus ket lambda m will also be a simultaneous eigenket of j square belonging to the same eigenvalue lambda, but of jz belonging to the eigenvalue m minus 2, and so on, provided we do not hit a null ket. But I have, so this is an arithmetical progression, m minus 1, m minus 2, m minus 3, and it can, if it goes on indefinitely, then this quantity will become much greater than lambda, and we have the inequality that lambda must be greater than m square. So, there must be a minimum value of m, and let that minimum value be equal to j prime. That means that ket lambda j prime is not a null ket, is not a null ket. However, j minus ket lambda j prime is a null ket, because then j prime is not a minimum value. So, once again this is not a null ket, this is not a null operator, but an operator operating on this will give you a null ket. So, let me multiply this by j plus, then my left hand side is equal to left hand side. So, this j plus j minus is equal to j x plus I j y, j x minus I j y. Let me do it carefully. So, we will have this is equal to j x square plus j y square, I times I is minus 1 minus minus plus 1, and then you will have minus I j x j y minus j y j x. So, this is I j z, actually I h cross j z. So, this will be I square is minus 1. So, plus. So, this will become j square minus j z square plus j z. So, this is my j plus j minus, but we have seen that j plus j minus operating on lambda j prime. So, this I operate on ket this whole thing, I operate this on lambda j prime. So, this will be a null ket. So, j square operating on this is an eigenket of j square. So, this will become lambda minus j prime square plus j prime operating on lambda j prime must be 0. This is not a null ket and this is a number now. So, this must be 0. So, this must be 0 and so therefore, lambda must be equal to j prime square minus j prime. So, this will be equal to j prime minus 1. In one of my, so please remember two things. Ket lambda m is a simultaneous eigenket of j square and j z. M is the eigenvalue of j z and lambda is the eigenvalue of j square. First, we derived that lambda must be greater than or equal to m square. Then we said what is the maximum value. So, we said that since this, because of this inequality, the maximum value of this is be j, and then we had found that lambda must be equal to j into j plus 1. Then we used ladder operators, j minus operators. We found that m must have a minimum value and let that be j prime, and we just now found that lambda must be equal to j prime into j prime minus 1. So, j prime into j prime minus 1 is equal to j into j plus 1. And since this is a quadratic equation in j prime, but since j prime has to be less than j, so the root is j prime is equal to minus j. Because if I put minus j here, so you will get minus j into minus j minus 1. So, that is j into j plus 1. So, the solution of this equation is j prime must be equal to minus j. So, the maximum value is j, the minimum value is minus j. And now see that I start with a value j and I go down in steps of 1, j minus 1, j minus 2, j minus 3, j minus 4, j minus 5, j minus 6, and then I must hit minus j. That is only possible if j itself is equal to 0, half, 1, 3 by 2, etc., not for any other number. Because we have said that if m is an eigenvalue, m plus 1 is also an eigenvalue. If m is an eigenvalue, m minus 1 is also an eigenvalue. It can hop in units of 1, and it has to land up on minus j. Otherwise, you will never get a null ket. And so, therefore, as you start with plus j, you hop in units of 1 and you go to minus j. That will only be possible if j takes these values. So, if you have j is equal to 1, then you start with 1, you decrease by 0, these are the m values. You start with j is equal to 3 by 2, so you have 3 by 2, half, minus half, and minus 3 by 2. Let me say that I take a, let us suppose I have j is equal to 7 by 3. So, 7 by 3 minus 1 is 4 by 3, 4 by 3 minus 1 is 1 by 3, 1 by 3 minus 1 is minus 2 by 3, minus 2 by 3 minus 1 is minus 5 by 3, and then minus 8 by 3, and so on. So, you have not hit minus 7 by 3. So, 7 by 3 is not possible. But if you use 5 by 2, so 5 by 2 minus 1 is 3 by 2, 3 by 2 is half, minus 3 by 2, and minus 5 by 2. So, that is possible. So, j is equal to 3, then 2, 1, 0, minus 1, minus 2, minus 3. So, we get the result that the value of j can only take 0, half, 1, and lambda is equal to j into j plus 1. These are the eigenvalues of the j square operator. Now, you see a remarkable result that we have obtained. Earlier we had said we had used the differential operator representation, and we had found that the eigenfunctions are the spherical harmonics, and the eigenvalues were L square y L m theta phi were equal to L into L plus 1 h cross square y L m theta phi. In fact, these were simultaneous eigenfunctions of L square and L z. But here L is equal to 0, 1, 2, 3, but here I will get that j square ket j m ket lambda m, this is equal to j into j plus 1 h cross square ket j m ket lambda m, and j z ket lambda m is equal to m h cross. But the difference between these two is that here j can take half integral values, and as we know that the electron and the proton and the neutron are endowed with a intrinsic angular momentum which is half h cross, and that is predicted by quantum mechanics, that we have now derived from quantum mechanics, and just by using commutation relations and nothing else. So, we finally obtain, actually instead of lambda, the convention is to label the eigenkets as ket Jm. This is not the eigenvalue. The eigenvalue is really lambda, but the convention is j square ket Jm. This is equal to j into j plus 1 h cross square ket Jm, and jz ket Jm is equal to m h cross ket Jm. I have put, so these and the values of j that we can take is 0, half, 1, 3 by 2, etc. And m can take from minus j to plus j. So, I had shown that j prime, which is the minus value of, which is the minimum value of j, was equal to minus j. So, therefore, these are the m values. For a given value of j, the m values go from j to minus j. I have now proved that just by using commutation relations. So, all the previous results are proved that because the differential operators also satisfy the same commutation relations. So, therefore, I have proved that for a given value of j, the m values go from j to minus j. Okay. Now, let me do one more algebra, and that is, we have shown that j plus ket Jm, if ket Jm is an eigenket of j square and jz, then j plus ket Jm is also an eigenket, but now belonging to the same eigenvalue lambda, which is j into j plus 1. Lambda is equal to j into j plus 1. But m value is raised. So, let me write this down as this must be a multiple of j m plus 1. Maybe you put a comma here. What we must always remember, on the right hand side I may write it down, that j square ket j m, let me write it on a fresh piece of paper, j square ket j m is equal to j into j plus 1, h cross square is there, but we assume that in a system of units where j h cross is 1, and jz jm is equal to m h cross is 1. We are working in a system of units with this. Now, we say that j plus jm, and these are orthonormal kets. These are simultaneous eigenkets, but they are orthonormal. That is, j prime m prime jm, they are all delta j prime delta m prime, they are all orthonormal, both of them, and this is normalized, that is jm is 1. We assume that because they belong to Hermitian operators. So, j plus ket jm is therefore a multiple of this ket j m plus 1. So, let this be C plus, therefore, let this be ket p. Then bra p is equal to bra jm j plus bar. This will be equal to, this is just a number. So, C plus star bra j m plus 1. So, I now write bra p ket p, this is equal to j m, j plus bar, you see j plus is equal to j x plus I j y. So, j plus bar is j minus, because this will be j x minus I j y. So, this is j minus j plus j m is equal to c plus mod square, and this is 1, this times this is 1. So, once again j minus j plus is equal to j x minus, this you must remember by now, j x plus I j y. So, this is j x square plus j y square plus I times j x j y minus j y j z. So, that is I times j z. So, this is j x square plus j y square is j square minus j z square minus j z. We have derived this earlier. So, we have therefore bra p ket p is therefore j m j square, j minus j plus is j square minus j z square minus j z operating on j m is equal to mod c plus square. So, this operating on this is an eigenket of j square, j z square and j z. So, j square of that will be j minus m square minus m, j m j m, this is c plus square. I am sorry, this will be j into j plus 1, I am sorry, j square, I am sorry, this is sorry, I have to write it again, j square operating on j into, this is j into j plus 1 minus m square minus m. This is not the eigenvalue, the eigenvalue is j into j plus 1 as we had done here, j into j plus 1. So, this will be j into j plus 1 minus m square minus m bra j m ket j m, which is 1 because they are orthonormal kets, this is equal to c plus square. So, this is equal to 1, and so therefore, we obtain c plus is equal to the under root of that. So, this will be j minus m into j plus m plus 1. So, therefore, j plus ket lambda m, I am sorry, let me do it again. So, therefore, we will have j plus ket j m will be equal to c plus, and that is square root of this, you have to remember j minus m j plus m plus 1 into j m plus 1. These are ladder operators, it raises the value of m to m plus 1, and similarly I leave it as an exercise. Exactly in a similar way, you show that the operator j minus m is proportional to j m minus 1, and this will be equal to j plus m, j plus m, j minus m plus 1. These two relations we have to remember, and we see that when m is equal to j, this is 0. So, j is the maximum value of m. So, j comma j is a non-null ket, that is a well defined ket, but j plus operating on j j is a null ket. Similarly, j minus j is a non-null ket, but j minus operating on that will be a null ket. That comes out automatically from here. Okay. Now, let me do an example. Let me consider the case where the spin half j is equal to half. This is an extremely important problem. So, j is equal to half. So, m can be only half and half minus half, sorry, m can be half and minus half. So, we can have only two states, state 1 which I denote as half comma half, this is the value of j. So, the eigenvalue of j square is j into j plus 1, half into half plus 1, that is 3 by 4 h cross square. So, j square ket 1 will be half into half plus 1, that is 3 by 4 h cross square ket 1, and j square and the other state will be ket 2 half ket minus half. Okay. Now, so these I take as the base vectors. I make a representation, I will try to make a representation of the operators j square, jx, jy, jz. Now, when you make a representation, you have to first tell me what are your base vectors. Like in an I want to describe a vector. If I want to describe a vector and in terms of its component, I will first ask you, tell me your x and y axis. So, those are the base vectors. So, in terms of the base vectors 1 and 2, I will write the operators as a matrix. So, for example, since this is a 2-dimensional space, there are only 2 base vectors, we will have 2 by 2 matrices. If I have j is equal to 1, where m can take 1, 0 and minus 1, so there will be 3 independent vectors and it will span a 3-dimensional space and you will have 3 by 3 matrices. So, of any operator, the matrix representation will be, let us suppose of operator p, there will be 4 numbers p 1 1, which is 1 p 1, p 1 2, that is 1 p 2, p 2 2 and p 2 1. These are the 4 numbers which will be a representation of the operator. So, let me take these as my base vectors. So, I will take ket 1. So, I consider j is equal to half, then m is equal to plus half and minus half. So, the base kets are half, half, and the second is half minus half. These are simultaneous eigenkets of j square and jx, that is j square ket 1 is equal to half into half plus 1, that is 3 by 4 h cross square ket 1, j square ket 2 is also 3 by 4 h cross square ket 2, and jz ket 1 is equal to, this is the eigenvalue of jz, half h cross ket 1 and jz ket 2 is equal to minus half h cross ket 2. Okay. Now, let me write down what is j plus ket 1. J plus ket 1 will be equal to j plus half half. So, this will be square root of j minus m. So, this is 0. So, you remember that j plus ket j m was, let me write it below, j plus ket j m was under root of j minus m into j plus m plus 1, j of m plus 1. So, this is 0 and j minus ket 1 will be j minus half half. So, this will be, please see this, j minus half half will be under root of j plus m into j minus m plus 1, j comma m minus 1. So, j is half, m is half. So, half plus half is 1, square root of 1, half minus half is 0, 1. So, this will be half minus half. So, that is ket 2. Now, let me write down what is j plus ket 2, j plus ket 2. So, here j is half, m is minus half. So, you get j minus m, half minus minus half, half plus half 1, half minus half is 0. So, this is equal to 1 and j minus ket 2, j minus ket 2 means m will go down, but that cannot be minus 3 by 2. So, this will be a null ket. Okay. So, we have all the relations now and we can now write down the matrices. First, let me write down for j square. So, if we have, first we wrote down j square ket 1 is equal to 3 by 4 h cross square ket 1, j square ket 2 is equal to 3 by 4 h cross square ket 2. So, j square, there will be 4 elements, 1 1, that is bra 1 j square ket 1. So, bra 1, so this will be equal to 3 by 4 h cross square. Then j square 1 2 will be bra 1 j square ket 2. So, this will be bra 1 ket 2. So, that will be 0. So, j square 2 1 will be 2 j square ket 1, that will be also 0, and j square 2 2 will be equal to, I leave it as an exercise. So, 3 by 4 h crosses. So, the matrix representation of the operator j square is 3 by 4 h cross square 1 0 0 1. Similarly, I have jz ket 1 is equal to half h cross ket 1, because m value is half, and jz ket 2 is equal to minus half h cross ket 2. So, again, since these are eigenkets, so if we write jz 1 1, so this will be multiplied by bra 1. So, this is half h cross, but jz 1 2 or 2 1, 2 1 will be bra 2 jz. So, this will be multiplied by half h cross. So, this will be 0 and jz 2 2 will be minus half h cross. So, the operator representation, the matrix representation of jz will be half h cross 1 0 0 minus 1. This is the sigma z, the sigma z Pauli matrix. We have derived that. What are the eigenvalues of j square at this matrix? 1 1. So, therefore, what are the eigenvalues of j square? That is just 3 by 4 h cross square. What are the eigenvalues of jz? The eigenvalue of this matrix are 1 and minus 1. So, the eigenvalues of jz are half h cross and minus half h cross. So, I will just give you a hint as to, and the rest we will do in our next lecture, that I want to now make a representation of x, jx. So, we have j plus is equal to jx plus ijy and j minus is equal to jx minus ijy. So, I add them up and I get jx is equal to half j plus plus j minus. So, jx bra m ket n, this is the mnth matrix element is given by this. So, this will be half m j plus ket n plus half m j minus ket n. I leave this as an exercise for you and we will try to do this next time, but if you can work this out, this will be very good, and you should find that the matrix representation of jx will come out to be half h cross 0 1 1 0, and similarly for jy. So, with this we conclude today's lecture, and what we have achieved is that we have been able to obtain the eigenvalue spectrum, simultaneous eigenkets of the operator j square and jz, and in our next lecture we will complete the analysis for obtaining the matrix representation of j square, jx, jy and jz. Thank you.